Hello, so in this little video we're going to talk about when you can compute a matrix product and what the size of that product is if you can compute it. Now in the last video we were multiplying 2 by 2 matrices, and I'll just do maybe a little example here. Say we had something like this. And so what we did is first we said, I just told you to kind of take it on faith that you can multiply a 2 by 2 matrix. 2 by 2 meaning, of course, 2 rows and 2 columns, and then here again 2 rows and 2 columns, that you can multiply them together and you'll get another 2 by 2. And the way you do it is that you take, to get the top left entry, for instance, I take the top row here, the left column here, I multiply the first entry here, the first entry here, the second entry here, the second entry here by each other, and then I add those together. So this would give me 2 times 8 is 16, 7 times 0 is 0, so that's giving me 16 plus 0 is 16 here. And then I could do the rest. I'm taking this top row right column for the top right entry here, so that would give me a 2 times a 1 plus a 7 times a 7, that's 2 plus 49 is 51. And then I would take the bottom row left column for this bottom left entry. 3 times 8 is 24, minus 1 times 0 is 0, so we got a 24 there. And then bottom and right for the bottom right entry here. 3 times 1 is 1, minus 1 times 7 is minus 7. Add those together and I get a minus 4. So that's what we were doing before. But the question is, when can you do this? For what sizes of matrices? Because there's all kinds of different sizes of matrices. I mean, over here, I've drawn matrices of different sizes. The case we were doing was the one down here where they both have 2 rows and 2 columns. But there's other cases. And you see, I wrote some cases here, this one and this one, where I'm saying that the product doesn't even exist. So what does that mean? Well, for the product to exist, you have to have the size of the rows in this first matrix here. So there's this row size. It's going to have to match what the column size in the second matrix is, because I have to match up the first entry of this row to the first entry of this column, the first entry of this row to the first entry of this column, and so on. Now this could be generalized to larger matrices. For instance, I could have, say I have a matrix that has, say, it has rows that have 7 entries in it. So say I have 2, 3, 0, 6, 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, and then I could put, a bunch of other entries down here. So I have this big matrix here. It has 2 rows, but 7 columns. Well, if there's any way I'm going to match up a row here, entry by entry, with a column in some matrix I want to multiply it by, well, then that column had better have 7 entries as well. So, for instance, I could put 3 minus 2, 1, 6, 2, 1, 8, 1, 2, 3, 4, 5, 6, 7, and then it would work. Now, of course, in this case, so if I just did it like this, then this would be this one would be well, it would have 7 rows, 1, 2, 3, 4, 5, 6, 7, 7 rows. It would have just 1 column here. And so you see, if I put these side by side, the 7, so the second number here matches the first number here. They have to match, because if they don't, then the size of this row is bigger than the size of this column, and I can't match up the numbers. So I want to match up this number with this number, and this number with this number, and I'm making it really messy now, but there's a reason for that. This number and this number, this one and this one. I want to match up the first one of this, the first one of that, the second one with the second, the third with the third, the fourth with the fourth. If one of them runs out before the other one does, it doesn't make any sense. I can't multiply them together using this procedure. So there's a special requirement for what sizes of matrices you can multiply together. And let me write out for you what that rule is. So now this seems kind of abstract the way I write it, but I've already explained what the reasoning behind it is. So the product of a, now I'm going to use letters to tell you what these numbers are, M by N matrix. In that last example I did, this was 2 by 7, remember, because the 2 was the number of rows, and then it had 7 columns. So that's what it was there. The product of an M by N matrix, now this doesn't have to be, of course, 2 by 7 in general, it just was in that example. The product of an M by N matrix and a K by L matrix, and of course in this particular case, the K by L, that was, it was 7 rows and 1 column, because it just had that 1 column there, and then 7 rows, 1, 2, 3, 4, 5, 6, 7. And once again, that doesn't have to be true in general, it's just it was in that example. The product of an M by N matrix and a K by L matrix exists if what? Well, remember we had a 2 by 7 and a 7 by 1. And I told you that the second number here had better agree with the first number here, because the second number there is telling you how many columns there are, which is the same as how big is a row, how many entries are there in a row. And the first number here is telling you how big is a column, which is the same as how many rows are there. So what we're going to say here is that the N has to be the same as the K. So this is if N equals K. And then this next thing I'm going to say wasn't obvious from the example we just did, because we didn't work it through entirely. But you can also tell if it does exist, if the product does exist, you can tell how big it is. So the product of an M by N and a K times L matrix exists if N equals K. And if it does exist, its size is, we're going to take the first number here and the last number here. This will be M by L. So that's the rule. Now the examples that we've seen so far, we had these 2 by 2 examples. And so we had, I don't remember what the numbers were, so I'll just make up another one. So we had, say we have something like this. Well, this is a 2 by 2. This is a 2 by 2. The product does exist. Why? Well, because the middle numbers here match up. Remember, so if this is the M by N, this is the K by L, the middle numbers add up. They match up, I mean. So that's the N equals K. That's this part here. These have to equal each other. And then what's the size? Well, we see the size here is 2 by 2 again. And that's the outside numbers, the M and the L, and that's this here. So you see that was true in this example that we did. And then the other one that I just started writing it out, where we had, something where it was bigger. So we had 7 columns. So we had this, this size here was 7. This size here was 2. And then we had just the 1 column here. So this size here was 1. And this size here was 7. So this matrix here, of course, was 2 rows, 7 columns. This one here was 7 rows, 1 column. Well, what would happen, first of all, the product exists because the middle numbers match up. That's my N equals K, because here we have M by N, and here we have, this is the K by L. And then what the size of it is, it's pretty small, actually. It collapses to give you something small. The size ends up being 2 by 1. That's the M and the L there. That's the M and the L here. So those were kind of the two examples that we saw. Now over on the right part of the board, I have a bunch of cases written out. And they're written out in generality because they have, they're written with letters. Now what do these letters represent? Let's look at the top one here. I have two matrices, and each of those matrices has just one entry in it. They're one by one matrices. So we have here we have a one by one, and here we have another one by one. Well, the middle numbers agree, the 1 and the 1 agree, so the product does exist. And the size of the product is given by the outside numbers, the 1 and the 1 out here. It's a 1 by 1, and that's that over there. And if you want to think of it this way, so this is also going to give you 1 by 1. If you want to think of it this way, you could say, okay, well, I take the A11, I take the, B11, and this is the first row. It only has one row, it only has one column, but I can still think of it this way. So I take the first row of this one, I take the first column of this one, I multiply them together, A11, B11, and that's giving me the only entry there is in that matrix. Now, why am I complicating this by writing these letters with these numbers underneath it? Well, it's because the numbers are telling you where in the matrix each of those letters lives, each of those entries lives. These just stand for numbers. I mean, in this case, I could have, this could have been a -2. This could have been an 8, for example. I can't seem to draw my 8s accurately. That could have been an 8. They just stand for numbers. But the way I have the formulas written out here, they're general formulas. They're true for whatever numbers you put in for the letters. So that was that first example there. We multiply a 1 by 1 matrix and another 1 by 1 matrix. The product exists, and we get a 1 by 1. This second one here, what do we have? 1 row, 2 columns. This is a 1 by 2. This has 2 rows, 1, 2 rows, 1 column. This is a 2 by 1. The middle numbers agree, so the product will exist. The size of it's given by the outside numbers, the 1 and the 1. It's a 1 by 1, so that's a 1 by 1 here. And you can see, yeah, that's what it is. It's just a number. Now, it looks kind of complicated here because it's given by 4 numbers, this one, this one, this one, and this one. Multiply these two together, multiply these two together, add the result. But really, it's a simpler example of what we've already been doing. I mean, I could take one with numbers that just looks like this. Say 2, 6, and then -10, 1, for instance. Multiplying these together, well, I take the first row, there only is one row. The first column, there only is one column. See, it's quite simple. I take the first entry here, the first entry here, multiply those together, 2 times -10. Second entry, 6 times 1, add them together. That gives me a -20. That gives me a 6, and they add together to give me a -14. And that's the only entry. So the product of these things is just a 1 by 1 matrix that has a -14 in it. So we looked at this case, we looked at this case. This case is different than this one. It's like kind of reversing those, and you get a totally different answer. And you get a different size, you get a different kind of answer because you have a different size of matrix. See, this has now 4 entries. It has 2 rows and 2 columns. 1, 2, 3, 4 entries. Why? Well, this matrix here it has 2 rows and 1 column. This has 1 row and 2 columns. The inside numbers match, so the product exists. But the size is given by the outside numbers, the 2 and the 2. That's given us a 2 by 2 matrix over here. And you can see that that's what it comes out to be. Now, the way you would do the mechanics of that is quite familiar. For instance, I could just write, just make up some. -1 and 7 here. 13 and 4 here. I take the first row. Now the row has only one entry, but that's fine. I take the first row here, the first column here. So this is the top row, left column. This is going to give us a minus 13 here. I take the top row, the right column, next for this next one. So forget about this now. I'm taking that one. I'm taking this column here, minus 1 times 4, minus 4. And then now forget about that. I'm taking the bottom row, left column, 7 times 13, 91. And then I'm taking the bottom row in the right column. 7 times 4 is 28. And you see that works out to a 2 by 2 the way you expect here. So we did that one, we did that one, we did this one here. We did this one down here, of course. That's the one we were doing at first. So I'm just going to say a brief word and then we'll be done. Just say a brief word about these two cases here where I'm saying that the product doesn't exist. Why is that true? Well, let's look at an example of this here. So I'm going to take the same sizes of things, but I'm going to put in numbers. Let's put in 3, minus 2, 5, 4 here. And then over here, I'm going to put a 7 and a 10, for instance. Now, suppose I try to play the same game. I take the top row, and I take the left column because I want to find a top left entry over here. I would assume there's some matrix there, and I would want to find what the entries are. Well, I match the 3 with the 7 here, but then I have this minus 2 here. What do I do with that? There's nothing to match it with. There's nothing. The row or the column has only one entry. There's no other entry to match that with. So it doesn't make sense. It doesn't work. It doesn't fit. This would be like if you're cooking or you're doing something and you try to add units of measure which are different. Like say I try to add inches to tablespoons. It doesn't make any sense. Or if you say, you wouldn't add your height to your weight. You wouldn't say I was 6 feet 2 inches tall and I got a pound taller. You get a pound heavier. You're measuring things. It's things that they don't compare to each other properly. The only way they can compare to each other properly is if this condition here holds, this n equals k. So that's telling you, what that's telling you is the length of each row in the first matrix has to be the same as the height of each column in the second matrix. And that's the case in which the product will exist. And then, of course, you tell what the size of the product is by those other two numbers. Now you really should know how to multiply matrices.